Okay, so today we're going to do one of my favorite topics in the whole course. It's just a short little bit, but on the other hand, it's something that is both surprising and easily demonstrated. So that's nice. Okay, so it's called, as you can see, Simpson's paradox, and the basic idea is that we sometimes have to decide whether to consider data that is aggregated or divided. So if we have, for example, a class of elementary school students, we have to decide whether to consider all the students at once or whether to consider them broken up, let's say, into boys and girls. So let's see. Here's a straightforward numerical example. It's obviously a made-up example, but the point of this example is to demonstrate to you something that a person's first reaction is, this is obviously impossible, and then I'm going to give you some numbers, and the numbers don't lie. So it's not impossible. In fact, it happens, and in fact, it happens all the time. It's one of these things where once you're tuned into it, once you think to look for it, you see it all the time. Okay. So Bob and Fred go to the track. They are having an argument over which is better, which person does better at the track. If we break into two categories, then Fred beats Bob in both categories. So long odds and short odds. Long odds is more than 2 to 1, but it doesn't matter. On long odds, Bob has won 0 races out of 1. So Bob has bet on one race and didn't win it. So that's obviously 0% win. Fred, on the other hand, has won one race out of 99. So not good, but better than Bob. So Fred is better than Bob on long odds. On short odds, it's shorter than 2 to 1, but again, it doesn't really matter. On short odds, Bob has won 50 out of 99 bets. Notice that's a total of 100 to make the numbers easy to do. So Bob has won 50 out of 99. My calculator says that's 0.51. Fred, on the other hand, has won 1 out of 1. And again, you notice that Fred has bet on a total of 100 races. So Fred has won 1 out of 1. That's 100%. So Fred is better than Bob on short odds. Fred is better than Bob on long odds. Isn't it clear that Fred is better than Bob? No, it isn't clear, because look at what happens when you take the total for Bob. Bob has bet a total of 100 races and won 50 of them. Fred has bet a total of 100 races and won 2 of them. Bob is way better than Fred. No, did I say that? Yes, Bob is way better than Fred when you put the categories together. So Simpson's paradox is that comparisons that hold when the data is divided into two, in this case into long and short odds, comparisons that hold when the data is divided into groups may reverse when you combine the groups. So you have to decide which is the right way to study the two, combined, that is aggregated, or disaggregated or split up. It seems clear that if Bob is better than Fred at both, if Fred is better than Bob at both categories, then Fred has to be better than Bob when you put the categories together. But it's not so. I mean, look at the numbers. There's numbers. There's no sleight of hand here, whatever. Now, a person can say, well, this is some kind of mathematical foolishness and doesn't happen in real life. Happens all the time in real life. I see it lots and lots of places. I'm going to give you a couple of examples. Could give you dozens of examples. Going to give you a couple just to try to convince you that this isn't just some mathematical baloney that never actually happens. So the National Assessment of Educational Progress is what it sounds like. It's some nationwide study of how various high school age, headed in toward college age, students are doing on mathematics, which we all know is the most important subject. So here we go. Okay. So overall, math scores for 17-year-olds decreased by a point between 1992 and 2012. Now that's 20 years. 20 years of hearing people saying it's important math. We have to increase the ability of students to. So 20 years of hard effort, and overall, here, this line right here, can you see it's the second one down from the top? This curve. So overall, the scores on their test that they give for their study, the scores have decreased by a point. But if you look at broken down into categories, white students, Hispanic students, black students, if you look at it broken down into categories, can you see that this up here is white students have risen, Hispanic students have risen, black students have risen. So when you break it into three categories, we're doing better. When you combine the categories into one, we're doing worse. What's the explanation? How's that possible? It's just like Bob and Fred. How is it possible that when you put the categories together, something different happens than when you break them into separate categories? And the answer, of course, is Simpson's paradox. But here, the explanation in this particular case is how is it possible? And the answer is the composition of students changed. In 1992, 75% of the students were white, and you can see that white students do better on this particular test. In 1992, 75% of students were white, 15% were black, and 7% of students were Hispanic. By 2012, 20 years later, we're looking at the whole sort of majority minority thing. 57% were white, 13% were black, 22% were Hispanic. So basically, Hispanic tripled, for example, and white went down by a good almost a third. So the composition of students in the mix is different. So you're more influenced, in the second case, you're more influenced by the scores of black students and Hispanic students simply because they comprise a larger number of the cases. So when you put the categories together, the larger numbers influence the overall more than they used to, and it ends up in a net loss of a point. But stepping back from the details of the 1, 2, 3s, stepping back from that for a second, this is Simpson's paradox. You have to decide when we're going to study how we're doing on the National Assessment of Educational Progress. Are we going to study it everybody all together, or are we going to study it broken down into groups? Because you get different conclusions when you do the two different things. It sounds impossible, but it's true. I mean, here's the numbers. They don't lie. Another example, again, I could give you a dozen examples. I won't trouble you with. I could give you hundreds of examples. I won't trouble you with hundreds of examples. But just to give you enough to persuade you that this is not some mathematical sleight of hand. This absolutely happens all the time. University of California at Berkeley is one of the top graduate schools in the world. The sort of future leaders of the world, CEOs of Fortune 500 companies, governors, presidents, all heads of department of the cabinet, lots of people, University of California at Berkeley. So this very important who gets in there. And the University of California at Berkeley was sued for bias against women who had applied for admission to graduate school. Here's the overall data. Look at this. It's very straightforward. Men were admitted 44%. Women were admitted 35%. It seems very straightforward. But of course, I wouldn't be doing it if it was very straightforward. And the answer is when you disaggregate into the separate graduate schools, it's an entirely different story. So there are 1, 2, 3, 4, 5, 6 different graduate schools. Law, medicine, this kind of stuff. When you disaggregate into the different graduate schools, let's look at graduate school A. Men is 62% admitted, women is 82% admitted. For B, men is 63% admitted, women is 68% admitted. C, men is 37% admitted, women is 34% admitted. Now that's a few fewer women, that's true. D, men is 33% admitted, women is 35% admitted. E, 28 versus 24, again, a few fewer women. And F, 6 versus 7. So what the heck is happening here? Is that here, very straightforward, perfectly clear. Here, not straightforward. And in fact, if I had to make a bid, I would say maybe there's a slight bias in the favor of women. I'm not sure I would say that, but it at least seems like there's more cases that are women than men. It's very complicated. So how is that possible? And the answer is, of course, in those graduate schools where women are admitted at a higher rate, you're looking, for example, at A, there's 825 men, 108 women, so there's a lower number of cases involved. Likewise with B, there's only 25 women, 560 men. So there's a lower number of cases involved. It's true they're brought in at a higher rate, but there's fewer of them. So stepping back again from the 1, 2, 3s, when you take the data all grouped together, you come to one conclusion. When you take the data disaggregated, I'm not sure you come to the other conclusion, but you at least say to yourself something like, it's not perfectly clear, is it? And I'm going to bring this around to sort of something that everybody knows. Everybody knows that in the U.S., and lots of other countries too, but anyway, everybody knows that in the U.S., women's pay averages significantly less than men's pay. However, while in total women earn significantly less than men on a per hour basis. In many occupations, women and men are not at all very different with respect to their pay. If you look, for example, at women managers of grocery stores, if you look at versus men managers of grocery stores, if you look at women who are dentists versus men who are dentists, if you look at women who run daycares versus men who run daycares, the question becomes, it's like the question with the graduate school, the question becomes much less clear. It starts to look like women and men are on an occupation by occupation basis at least competitive. So please, I am not claiming. I am not claiming that there is not gender discrimination. I'm not claiming that at all. All I'm saying is that to understand the conversation in the sort of civic space, you have to understand Simpson's paradox. How is it possible that one side can say overall women make much less, and the other side can say occupation by occupation they tend to be very much equal, and both sides are right? Both sides have the numbers to back themselves up. How's that possible? And the answer is Simpson's paradox. But going a little more into detail, when you say men daycare owners make the same as women daycare owners, there are no men daycare owners. I mean, there's very, very few. When you say men brain surgeons make the same as women brain surgeons, well, there tend to be many more men brain surgeons. So that's to say there's a mix of a different kind. And a person can very sensibly argue that the jobs that tend to be lower paid are often traditionally thought of as women's jobs. And I'll just mention elementary school teacher, for example. The jobs that tend to be lower paid are very often the kinds of ones that we associate with women, and daycare is an example. But nonetheless, so I'm not claiming to settle the question. I'm only claiming that for a person to understand what the argument is, you have to understand how it's possible. For you put the data together, you come to one conclusion. You break it out into separate categories, you come to a different conclusion. How's that possible? And the answer is Simpson's paradox. Okay, very good. So kind of a fun topic where you come to an interesting point very quickly, and with just a few numbers, and has to do with comparing the statistics. So I like it for this question. Okay, very good.